So hi everyone, and welcome to today's class. And in the previous class, we looked at hypothesis testing for independent samples. But you notice that there are many cases when that is the assumption of independence is violated. And this in many cases happens when you have or you take measurements from the same individual on different occasions. For instance, you may take the weights of some individuals at some point in time, then they undergo some treatment or some diet, or maybe through some therapy, some exercises, and then you check their weights after that. You notice that the first set of observations is very much related with or correlated with the second set of observations. So those are what we call paired samples or dependent, which end up being dependent samples. So we can start by introducing the course by the lesson by saying that when testing for the difference between two means, the use of independent samples can have a major drawback or limitation. So even if a real difference does exist, the variability among the responses within each sample can be large enough to hide it or to mask it. So the random variation within the samples will mask the real difference between the populations from which they come. So one way to control this variability, which is in this case external to the question, to the research question, is to use a pair of responses from each subject and then work out the differences within the pairs. And the aim of doing that is to remove as much as possible the within subject or subject to subject variation from the analysis. And by doing so, you end up with the actual difference between the two population means. So the assumption that we're going to make here is that the difference between the two samples constitutes a random sample from a normal population. And as we illustrated here, you have let's say these are the individuals. You have, let's say, some 5 individuals. Then you measure your weight at some point T1. So you have the weights here. Let's say 1, like that for the different time periods. Then after that, you'll have some treatment. So in between the measurement, there must be some intervention here. So there's some intervention or treatment in between the two measurements. Then after that, we'll come and measure their, so WT2, you measure the weights of the same individual. So you can have weight 2, weight 3, 2, weight, let's say 4, 2, weight 5, 2. So you notice that the observations W11 and W12 are very much related because they are coming from the same person of the same individual. So in such situations, it is better to start by working out the difference. So the difference between, let's say, so I can, for convenience, I can label this one X and this one Y. So for convenience, I label them like that. So we're saying that a better way is to look at the difference between the pairs of observations, which I'm calling D here, where D is equal to Xi minus Yi. Then now you work out with the differences obtained from here. And the assumption is that we assume that the difference constitutes a random sample. These are the differences. They constitute a random sample from a normal distribution. And in that case, we'll be testing the null hypothesis that H0, that mu of D is equal to some hypothetical constant delta, where mu of D is the difference between the population means, mu1 minus mu2, which are the difference between the hypothetical population means for the paired observations. And then delta is a hypothetical constant. It can be 0, it can be some other non-zero value. Then in that case, the test statistic is defined as shown here, where we said that this is analogous to what we have been using in the case of single samples, where you say that T is given by X bar minus mu over S over root N, where X bar here is corresponding to D bar. So that means we need to get the mean of these differences. So we need to sum them. You sum the DIs. So you need to get D bar, which is summation of the DIs divided by N. That's the mean of the sample differences. And then we have S of D, which is the standard deviation of these differences. So you find the standard deviation of these values, standard deviation of those values. Then of course, N is the size of the sample. And then delta is, as explained earlier on, is the hypothetical population difference. Okay. Then we are saying that when the size of the sample is large, the assumption of normality is not necessary. You can deal without it, based on the central limit theorem. Based on the central limit theorem. Okay. Then we have some example here, and we're saying that the average blood pressure B bar. So the average is analogous to the arithmetic mean. For a group of 10 patients was 77 units. And then the average blood pressure, A bar, after they were put on a special diet. So you see there's some treatment in between the measurements. They were put on some special diet. So that's like the treatment. So the average blood pressure was 75 units. You're asked to carry out a statistical test to assess whether the special diet reduces blood pressure. And then you are given this information. Summation of BI minus AI squared for the 10 individuals is 68. So solution, and before we solve, I want us to visualize a scenario like this, where we have some 10 individuals, 1, 2, all the way to 10. And then we have their measurements before. So we can have it the BIs. So we have values here. So we have B1, B2, all the way to B10. Then we also have their measurements after AI. So we have A1, A2, all the way to A10. Okay, so because the individuals are the same, just like we explained a little bit earlier, is that their measurements will be very much correlated. So we need to work out the difference, the DI. So the difference between B's and the I's. So we have BI minus AI. But here in the information given, we are given this information squared. So I can just have another column here. I can have another column here for BI minus AI squared. So this is what we are given in the question, BI minus AI squared. Okay, so that information will be useful when we are calculating the standard deviation for the differences. So at some point we'll need the mean of the differences, and because we know that the difference is given by BI minus AI, we can introduce summations both sides. If we introduce summation here, we also introduce summation here, and then summation there, divide by n everywhere like that. We'll see that on the left hand side we have D bar, the mean of the differences, which is given by, if you take summation of the B's, divide by n, you will get the mean of the B's, then minus the mean of the S. And we are already given that in the stories. We are already given the mean of the B's and the mean of the S. So it is easy for us to obtain the mean of, the mean of the differences. So I think we have all the information that we need in order to solve this question. So let's solve the question. We start by saying that we are testing the hypothesis. We are testing the hypothesis that H naught, that mu of the first population is equal to mu of the second population. Okay, that means that our delta in this case is equal to 0. So we're saying that mu of the difference of the means is equal to 0. So that's what we are trying to do here. So we're doing that against the hypothesis that that is always given in the question. Carry out a test to assess whether the special diet reduces the blood pressure. So that means that our H1 will be mu A is less than mu of B. So which is calling for a lower tail test. All right. Then we say that if we assume that blood pressures, are normally distributed, then under the null hypothesis, the DIs, and of course we have said what are the DIs. The DIs are here. The DIs also have a normal distribution. Which is a very important statement there. Okay, so we can apply a one sample. So we can apply a one sample t-test to the Ds, to the DIs, based on the sample variance, S squared of D. So we're using a t-test because, of course, the population variance or standard deviation is not known. So, but from the information given, it is easy for us to get the sample variance of the differences. Okay. So, from the given information, and from what we've just said up there, is that D bar is equal to which one is starting? A bar minus B bar. It doesn't matter. So we have reversed them, which is equal to 75 minus 77, which is minus 2. Okay. Then S squared of the difference. So remember, we have some data that looks like this. So we have a table like this in our background. So we're trying to find the variance of this. Variance of DI. Variance of DI is what you're calling S squared of D. And for you to find the mean of this, you'll be taking these values minus the mean. So we talk about, you take the DIs minus the D bar, then you square, you sum, divide by n minus 1. If you want to find the variance of that column. Okay, we already have this. Then we know that, so let me write that. So we know that we can write that formula in a different way. So this is given by, so this will be given by summation. If you sum all of them, then you take your DI minus D bar squared, divide everything by n minus 1. But we know that we can write this formula in this format: summation of I is equal to 1 all the way to 10 of DI squared minus n D bar squared. So this is the guy that is only squared, divided by n minus 1. You just need to recall that you may not want to write this. If you are given this, if you are looking for this is a summation of x minus x bar squared over n minus 1. Remember, we can rewrite this in the format summation of x squared minus n x bar squared divided by n minus 1. So that's the same logic we're using there. Okay. And we note that from the information given, we know that DI is equal to, we have reversed the order, DI. So that means that DI squared will be equal to AI minus BI squared, which implies that summation of DI squared is the same as summation of AI minus BI squared. So this item here, This item here is what we are given in the question. This item there, summation of di squared, is the same as this. And that's what we are given in the question. That's what we are given in the question. Then we know n is the number of observations, and clearly there are 10. Then d bar is what we've just obtained here. D bar is here. D bar is there. So that means that now we can obtain our variance of the differences. So that means that SD is equal to, you will take 68 minus, you take a 10, then minus 2 squared divided by 10 minus 1, which is 9. So that's how you get the variance of those differences. The variance of those differences. And when you use your calculator, you will get around something like that. You will get something like that. Okay. So from there, once you have the sample mean of the differences, and of course the variance of the differences, now we can calculate the test statistic. So our test statistic here, clearly because our sample is small, we shall be using the t distribution. And already we have made an assumption that we are assuming that the population from where the samples are coming from, the populations are normal. So we shall comfortably use the t distribution. Will be given by d bar minus delta divided by s of d over root n. Okay. So we can also say that, which implies that if you take s of d, you take the square root of 3.11 into 3.11, you'll get 1.7638, something like that. Okay, so this is equal to d bar, which you've observed is minus 2, and delta, remember, this is the hypothetical value, the value that is used in the hypothesis, in the null hypothesis, or in the hypothesis statement. So in our case here, this means that if you are to take mu A minus mu of B, this is our delta. And in this case, we are saying it is equal to 0. If you are testing whether they are equal, it means that you are testing whether the difference between the two is equal to 0. So please note that. So coming to our statistic, we have minus a 0 divided by 1.764 divided by square root of 10. So that is our test statistic. So that's our divisor there. And your t value will be minus 3.59. Minus 3.59. So that is a value that we'll be using in your hypothesis testing. Okay, so let's get the critical region. As we mentioned earlier, this will be a lower tail test. So we'll be dealing with something like that. Then you put the entire critical on one side. So assuming alpha is 5%, because we said that by default you use that, the degrees of freedom in this case will be 10 minus 1. We can obtain the critical value from the t distribution tables. But I want to use R so as to get it very quickly. All right, so when you use R to quickly obtain the critical value, it will be QT 0.05, 9 degrees of freedom. So the critical value is minus 1.833. So that's the value we put here, minus 1.833. So comparing that with this value, we notice that this is the critical value. Then the calculated value will be deep in the rejection region. This is minus 3.59. This is the calculated value. So clearly we are going to reject the null hypothesis. So we say that the calculated statistic falls in the rejection region. It falls in the rejection region. So we have sufficient evidence. We have sufficient evidence to reject H naught, that mu A is equal to mu B at the 5% level of significance. So let's say this, to reject this in favor of H1, that that mu of A is less than mu of B at the 5% level of significance, sorry, like that. Therefore, it is reasonable. It is reasonable to conclude that the special diet reduces the blood pressure. It's reasonable to make such a conclusion. Based on the available information, we can make that conclusion. Okay. Any question? So let's look at this question that we'll try at home. And the question says that in order to increase the efficiency with which employees in a certain organization carry out a certain task, 5 employees are sent on a training course. The time in seconds to carry out the task, both before and after the training course, is given below for the 5 employees. So you have the data. And then the question is, test whether the training course has had the desired effect. So in short, there you are checking whether the time taken to complete the task has decreased, whether the time taken to complete the task has decreased. So you'll be checking whether the difference is actually a negative value. You're checking whether the difference is negative. If you take after minus before. If you take after minus before, you check whether that difference is negative. Or otherwise, you can just check whether if B minus A is a positive value. Okay, so we'll try that after class.